Years back, when the king wanted to have a cold drink, he would order his servants to go to the hilltop and get ice for him. The servants would bring back big blocks of ice. But by the time these reached the king, only a small piece would be left. And if the king was not satisfied and ordered for more, well, it could create panic. So what happened to the ice? Where did it vanish? Well, we know it melted. This process of melting is also known as fusion. This is something that you observe every day. When you take out an ice tray and the ice cubes, if you leave them for some time, they melt. So this is what is happening in the freezer. When you take out ice, the temperature of ice is, say, negative 30 degrees Celsius, and the room temperature is 25 degrees Celsius. Something like this happened when the servant was bringing back ice to the king. So the temperature at the hilltop was minus 30 degrees Celsius, and when he was bringing back to the king, the temperature was 35 degrees Celsius. How is the change of temperature related to the melting of the ice? Let's see. So this temperature is also the heat energy. As the temperature increases, more is the heat energy. If more is the heat energy of the particles, this heat energy is converted to the kinetic energy. This conversion of heat energy of the particles to the kinetic energy, and we know that kinetic energy and speed are related. Greater is the kinetic energy of particles, greater is the speed. So more is the temperature, more the kinetic energy. Greater is the speed. So is it vice versa? Lesser the temperature, lesser the kinetic energy, and lesser the speed. Let's see what happens during melting. So we have ice, or the solid form, at negative 30 degrees Celsius, and the temperature of water at room temperature, it's 25 degrees Celsius. So there is increase of temperature, that is, you're providing heat to the ice. So when we provide heat to ice, which is in the solid form, so this heat gets converted to the kinetic energy. Now, greater the kinetic energy, greater is the speed of the particles. Thus, they start vibrating with a greater speed. As they move at a greater speed, they move away from each other. This increases the interparticle space. Interparticle or the intermolecular space increases. The intermolecular force decreases. Therefore, they overcome the force of attraction, and so the solid form changes into the liquid state. And this is all melting. Let's revisit the concept of melting. So as the temperature increases, that is, as you provide heat energy, the heat energy gets converted into kinetic energy. So the kinetic energy of the particles increases. This increases the speed of the particles. As the particles move at a greater speed, they move away from each other. So the interparticle space increases. This decreases the interparticle forces of attraction. And so the solid changes into the liquid. And this is how melting takes place. What do you think is the melting point of ice? So the temperature of ice, when you take it out of the freezer, it's minus 30 temperature, and it changes to the water at room temperature. Is the melting point of ice minus 30 degrees Celsius, 25 degrees Celsius, or 0 degrees Celsius, or none of the above? Let's perform an experiment. Let's check the melting point of ice. So we take some ice cubes in a beaker and we heat it. There's a thermometer to check the melting point of ice, at which the solid ice changes into liquid water. As we heat it, the temperature from negative 10 degrees Celsius rises to 0 degrees Celsius. At 0 degrees Celsius, the entire ice changes into water. So from the experiment, we saw the ice melted to form water at 0 degrees Celsius, and this temperature at which ice melts to form water is known as the melting point of ice. So the melting point of ice is 0 degrees Celsius. The melting point is defined as the constant temperature at which a solid melts to become a liquid at the atmospheric temperature. Atmospheric pressure. These temperature calculations are made at constant pressure change. That is, at the atmospheric pressure, because within the change in pressure, the melting point also changes. So these calculations are always made at a constant pressure. That is the atmospheric pressure. Let's revisit the experiment which we had performed. We've already seen that the melting point of ice is 0 degrees Celsius. Try to observe something else here. As we heat the ice cubes, initially the temperature rises from negative 10 degrees Celsius to 0 degrees Celsius. Then it stays for as long as the entire ice is changing into water. The temperature does not change till the entire ice changes into water. When the entire amount of ice present in the beaker changes into water, the temperature again gradually increases from 0 degrees Celsius. So here you saw that there was a change from negative 10 degrees Celsius to 0. The temperature remained at 0 degrees Celsius till the entire ice changed into water, and then the temperature started to rise again. This heat, a latent heat, latent means hidden. This is the heat which is hidden in the solid, that is in the ice. It is the entire amount of heat which is required for the change of state. So when it's changing the water, the temperature remains constant. At 0 degrees Celsius, still the entire ice changes into water. As soon as the entire ice changes into water, the temperature starts to rise again. So this heat, the latent heat or the hidden heat, is the amount of heat which is required for the change of state, that this from the solid to the liquid. So we saw that melting is a change from solid to the liquid state. Similarly, freezing, it is also known as solidification. It is the change from the liquid state to the solid state. This is also something which you observe every day. When you fill your glass of water, you keep it in the freezer for some time, then take it out, and then you get a solid ice cubes. So we know as the temperature increases, the heat energy of the particles increase. This increases the kinetic energy of the particles, and so the speed of particles increases. So is it for the vice versa condition? That is, if we decrease the temperature or we remove the heat energy from the particles, its kinetic energy decreases. As the kinetic energy decreases, the speed of the particles decrease. So let's see how freezing takes place. So we have water at room temperature, say at 25 degrees Celsius. It's kept in the freezer, which is at negative 30 degrees Celsius, and we get ice. So you see there's a decrease in temperature. That is, we are extracting heat from the particles. So as heat energy is removed from the particles, their kinetic energy decreases. As their kinetic energy decreases, the speed of the particles decreases. So the particles come closer to each other. As the interparticle space decreases, the intermolecular forces of attraction increase. This tends to bring the particles very close to each other, and therefore the liquid form of water changes to the solid from ice form or ice. And this is how freezing takes place. Let's revisit the concept of freezing. So as the temperature decreases, that is, we are extracting heat from the particles, so the kinetic energy of the particles decrease. As the kinetic energy of the particles decreases, the speed of the particles decrease. This in turn leads to the decrease in the interparticle space between the particles, because of which the interparticle force of attraction between the particles increases, and therefore the liquid form changes into the solid form, and this is the freezing point. At the room temperature, say the temperature of water is 24 degrees Celsius. Inside the freezer where ice formation takes place, the temperature is negative 30 degrees Celsius, but the freezing point of water, that is the temperature at which water changes into ice, it is 0 degrees Celsius. If you notice, the melting point of ice was also 0 degrees Celsius. And the freezing point at the water is also 0 degrees Celsius. So for any substance, the melting point and freezing point are the same. So the freezing point is also defined as the constant temperature at which liquid changes into a solid at the atmospheric pressure. Because with the change in pressure, these values also change. So these calculations are made at a constant atmospheric pressure. So this is the constant temperature at which a liquid changes into the solid state. So here you have a solid sample. We provide heat to the sample. As you provide heat, you see the kinetic energy of particles increases. Therefore, the speed of the particles start to increase. The interparticle space between them, and therefore the interparticle force of the attraction between starts to decrease, and therefore the solid form is converted into the liquid form as we provide heat energy to the sample. Now let's say we have this liquid sample and we extract heat from the sample, that is, we cool it. As we cool this liquid, the kinetic energy of the particles decrease. The interparticle space between the particles decrease. The intermolecular forces, attraction between the particles start to increase, and therefore the liquid form is changed into the solid form when we extract heat. That is when we cool the sample. That is, so the conversion of solid to liquid, it's known as melting, and the change of liquid to solid is known as freezing.